Well, in this demonstration we are going to see the effect of a high gain in a feedback control system. Actually, high gains in the feedback control systems can actually eliminate a number of nonlinearities. Over here we have a specific type of a nonlinearity which is caused by some nonlinear elements in this circuit. They are dynamic-less. Now, the important thing is that what is a dynamic-less system? If you talk about it in true mathematics, a dynamic-less system is a system that doesn't involve the derivatives and integrals of different states in its input-output relationship. Well, if you ask electrical engineers or mechanical engineers about a dynamic-less system, they would say that it's a system that does not contain energy storing elements. Doesn't have any inertia, or doesn't have any capacitor, or doesn't have any energy storing element. And if we talk about what we call signals and systems, so in the terms of signals and systems, we would say that it is a system that is without any memory. It's a memory-less system. And such nonlinearities, they are very common in electrical systems. For example, in class B amplifier, crossover distortion has the same type of characteristics where they have a dead zone. One input is changing while the other input doesn't have any effect on the y-axis. The same type of nonlinearities appear in system biology. We have gene regulatory thresholds which behave in the same way. In the the signaling pathway of cell apoptosis, we have the same type of behavior where different enzymes need to have a threshold value in order to trigger the cell death process, the cell programmed death process. In the same way, in mechanical systems, we have one gear moving while the other gear is not moving because of the backlash in the gears. So these types of nonlinearities, they are very common in electrical, mechanical and other physical systems. Okay, well, now this is the block diagram of the system that we are going to use in this demonstration. We have this nonlinear element over here, and we have connected the system in a unity feedback, and we have over here a controller that can provide us with a gain. Now in this system, the gain will be ranging from 10 raised to power 3 to 10 raised to power 4, something like that. Now if we can make this arrangement work, then the relationship between the output and the input can be actually converted into a linear relationship. So this is the input-output relationship. We have actually a dead zone over here where this variable, the input, is changing, whereas the output is not changing. So we have a dead zone over here, and then the input starts changing as the output starts changing as we are going to change the input of the system. So this is basically the nonlinear relationship. Now you see in this block diagram, if I can change or apply this gain in the range of 10 raised to power 3 to 10 raised to power 4, something like that, 1000, 10,000 like that, then I can actually change this relationship into a straight line between the input and the output. This is what we can say. See in this demonstration that a very high gain can actually convert overall the nonlinear system into a linear relationship between the input and the output. Okay, well, similarly in this system you can see that we have a system where we have different disturbances adding into the system. We have D1, this is adding and at the same channel where the input is applied. For example, if this is an amplifier system, you can say that this is a disturbance, this is the ambient disturbance, maybe caused by some fan or by some refrigerator or by some AC. So this is entering at the same level where the input signal is being added into the system. So they are at the same channel. And then we have D2 that is added after A1. We can say that A1 is the pre-amplifier stage, and this is the noise that is, or disturbance that is added due to the pre-amplification. And similarly we have D3 added into the system. For example, in terms of amplifiers, this would be the power stage, and D3 is the noise that is added due to the power amplification stage, and then we have the feedback gain in the system. So if we can write the input and output relationship, we get equation like this. So in this equation you can see that the input signal and the disturbance D1, they appear at the same channel. Because they appear at the same channel, so they are not affected by A1 and A2. They cannot be eliminated by these gains A1 and A2. Whereas this disturbance D2, it is being divided by A1. So this means that if I increase this gain A1, I can eliminate the effect of D2. In the same way, by increasing the product A1 and A2, I can eliminate the effect of D3. So D3 disturbance can be eliminated if I increase the gain A2 and gain A1, or the product A1, A2. I can eliminate this noise or this disturbance also. So in this type of system where we have unwanted signals and disturbances added into the system due to preamplification or power amplification, such noises and disturbances can also be catered by high gain in the feedback control system. Okay, well, this is the nonlinear system that was under consideration, and you can see over here we have a nonlinearity in terms of a dead zone. Now what we are going to do is that we are going to introduce a feedback controller, a high gain feedback controller, into the circuit and see what is the behavior of the system. So I am going to shift the inputs, and now I am going to introduce a controller into the system. So I am just going to lower down the input values because of the controller, and you see the relationship between the input and the output has turned into a straight line. Now the important question is that where did the nonlinearities go, and how the controller is behaving to eliminate those nonlinearities. So if I just clip the oscilloscope and I just want to change the XY mode to the time domain mode so that I can see the signals. So this is the controller output. So over here what I see is that this is the controller output, and it's not a sine wave, it's a very non-linear type of behavior. Now you see the this is the controller effort, and this is the output of the controller in order to eliminate the non-linearities. Now you see I just changed the time scale. You see the controller effort over here. Actually this is the controller effort to eliminate the non-linearity that was actually present in terms of the dead zone or the backlash error in terms of gear assembly. Okay, so now over here there is a very important question. If I can represent the non-linearities by a matrix A, then this controller effort is a matrix B such that A times matrix B results in a unity matrix. That means that the controller effort or the controller matrix B is basically the inverse of the non-linearities of matrix A. So that the relationship or the overall relationship of the system from input to the output becomes a linear system. Now over here there is a question for you that is this system a feedback linearization? So can we say that this is a feedback linearized system?
No,
yes.
sir.
No. Okay, you're right. This is not feedback linearization, but as a term of assignment I would just like you to submit in my next lecture that why it is not feedback linearized system. So what is the difference between this system and a feedback linearized system? Thank you very much. This is all for today.